there off the top of my head. It's all about properties, I think, yeah, working with functions. And now we're going to look at how do we work with functions. So some of the other important aspects of function sets is needed for success in the calculus. Now the first section over here is we're going to use those groups of functions and bring them together or piece them together. And this is called the concept of piecewise functions. And what that means is our phenomena may have different things, like in an engineering or electrical engineering, you may hit a switch, and then you go from, say, a linear polynomial to maybe a quadratic polynomial. And you would like to see how that function looks. And you want to piece functions together. So piecewise functions or piecewise defined functions. Let's take a look at an example of what we mean by that. So here's my function. I say I found my function f of x. I'm going to define it not as a single function, one of those polynomials or something, but a couple of different polynomials. So sometimes you'll define it like this. And I'm going to say it's equal to, what do I want to do for that one? I was looking at this earlier. Okay, I'm going to say it's equal to x when I go from, say, minus 2 is less than x is less than 1. So on that interval, I want it to be this function x. Okay? And then after that, so it's a linear function, it's increasing, and then after that, I want it to then switch to a quadratic function. And let's let this be true for 1 is less than x, and is less than, let's just take it up to 2. So that's my new function. It's piecing together the linear function x and the parabola x squared. Well, how do I draw that? How do I sketch that? Okay, so let's come over here and see how we sketch it. So I'm going to go from negative 2 up to 2. Now notice I'm missing some points over here. I don't have equal to. That's going to be critical. So let's kind of do this over here. So here's my negative 1, negative 2, and here's my 1, and here's my 2. So I'm defined from negative 2 up to positive 2. That's the domain of this function is that minus, it's not 2, and it can't be 1. So I'm missing some points in the domain of this function over here. So what does this look like? Okay, from negative 2 up to positive 1, it is nothing more. I come over here, and kind of go over here, 1, 2. Not drawn perfectly to scale, I get as good as I can. It looks like this. This is my function, starts over here. It's an open circle. At negative 2, it's not defined. And it comes up all the way over here to 1, comma 1. Now, if I put in 1 for x, I get 1 for f of x or y. So that's this part of the function in blue. Then I continue with a different function. Now it happens that it crosses. When I put 1 in, I still get 1, 1, but it's still not defined there. So the next part of the function is my parabola. Remember, parabola would go like this, but it would come all the way up here, and it would continue to go as a parabola. So at 2, I'm over here at 4. And it's not defined there. So that is an open circle. So that's what my function looks like. And that point over there that's not on it is 2, comma 4, meaning I put in 2 in for x squared, and I get my y value of 4. So that's what it looks like. Now, sometimes you might see this. For example, say I wanted to be and include 1. Right now, this one has a hole here. Its domain is the domain of this function. Let me just put it here separately. The domain of that function is the following. The set of all elements x, that's at minus 2 is less than x is less than 1, and 1 is less than x is less than 2. That's the domain of this function. It has a hole at the ends and a hole in the middle. I can put any of the values, because, for example, if I say compute f of 1, this is where it gets a little subtle. So I say find f at 1. Well, what would I do? I'd look for, I'm going to get rid of that green for now. This is not defined for x equal to 1. That's not defined for x equal to 1. So the answer to that would be undefined. You didn't give me any instructions on how to compute it, so it is undefined. How do I represent that? With a hole in the function. At that point, there's a hole, it's undefined. And that's all it is. Now, if I wanted to define it, say at 1, I could say, okay, over here. And what would I do? Well, I just shade that in, and now it's defined at 1. And I could say at 1, it's equal to 1. So when x is 1, y is 1. Now, I could also define it over here if I wanted to. But sometimes you'll see it defined in a different way. I could define it this way. Let's bring this down just one more. And I say it's equal to 0 if x is equal to 2. So that little thing takes, when x is 2, my value is 0. So I go from that open hole. When I hit 2, I go shut off down to 0. That could be like a switch shutting off in an electrical engineering. This could be modeling some sort of an electrical phenomena. You close the switch, and it shuts everything off. Usually, it's not that instantaneous. This might be an estimate of something, but it could represent that. This is what we mean by a piecewise defined function. You take other functions and piece them together, creating your domain and your function. Now, this is also available under Desmos. Let me show you that as well. So, what I've done in the textbook, most of these things are under Desmos. And I'll have you try some of these things as we go. Here I have that same function set up with some other parameters. Take a look at what it is. If you y equal to, and you give the interval first. You give the domain values first. So it goes from minus 2 is less than x is less than 1. Okay? And then I put my semicolons over here. And then I put the function I'm using for that. The function I'm using for that then is x. And then I put the rest. I go now from x is from 1 up to 2, not inclusive. Put a comma between it. You have to have a comma. So this is my first piece, comma, my second piece, and then put my semicolon there. Pretty sure it's a semicolon. It looks like it's a full colon. Excuse me, it's a full colon. And then I put my second function, x squared. And then if I wanted to, I could label these over here. You come over here and you look at this. This is where you can create either, for some of these options over here. So you can either put a hole, this fills it in, that's a hole, that puts an X there, so over there, we use that as a hole for that one. And when we're done there, it leaves it as a hole. Now, if I wanted to include the other function, so over here, I think it's this way. I haven't tried this yet. So you have, for x equal to 2, then I put my full colon, and then I put in my 0 function. Let's see, is it going? Will it give it to me? There it did. It looks like it might have. I haven't tried this yet, so let's see how that goes. So it's not really showing to me, but if I plug in a value for it, I will get 0 down here. So over here, the function should be defined. And what I would do over here to do that, I would put in another, say 2, 0, just to show it. And what I would do is also change the color of that to make that black. You can make it different colors. I'm just making everything black, and that means I'm going to just color that in. So that should be it. And there it is. So that there's a hole over here, and it jumps down there. And there's a hole over here as well. So that kind of shows you, and there'd be some problems in the homework to practice doing this in Desmos. Because very often in the calculus, we are trying to model phenomena that is not continuous over space, or if instead of x over here, this was time, that might be modeling a time phenomenon. And it may have a certain behavior up until a point, and then it changes the behavior. It's hard to do that with some of those basic functions that we've given you. Maybe, for example, you might have something that starts out at a certain level. So you might want to model something like this. It starts out at a certain level. Say this is time and this is y. And there's a certain DC voltage. A switch is placed in place, and then you start modeling that with a sine wave. How do you capture that? The way to do that is with this concept of the piecewise defined function. Okay, so let me give you one to try and see if you can put it together. There's a lot of different pieces here that you have to kind of practice. So this is 4.1. We're working with these functions now. All those functions that we just created, those are our families of functions that we're going to be using to then create more complicated functions. So some of the phenomena we study may be quite complicated. We want to model as we can using all these different types of functions. Different types of functions are useful at modeling different types of phenomena, as we will see later on in the textbook when we look at some applications. So what I want you to do is, graph the piecewise defined function. So f of x is equal to the following. So let's say it's equal to 2x, and this is good for, minus 1 is less than or equal to x, which is less than 0. And let's say I do x squared plus 1, or x is less than or equal to 0, and up to, say, 1. And then I say it is maybe at 1 minus 2x, where x is greater than 1. I'm leaving a point out in particular. And let me just add one more here. Say x equal to, say, a positive 2 when x is equal to 1. See if you can piece together that piecewise defined function. I'll put it over here. In fact, I'll do the pieces in different color. I'll try and color coordinate them as best we can. So we're just going from minus 1 up to 1. Not quite the scale. We'll make it to scale. The vertical scale is about half the scale of the horizontal, just so we'll know that. This is a different scale on the y-axis versus the x-axis. See if you can sketch that out. I'll do the first part over here. In blue. I'll do this in blue. Right this way. I'll change that because I want to show you some different things. I'm making a change over here. That's a change over there. Just to kind of show you what's happening. So this is a blue. That's red. I'll do this little guy here in green, just so you can kind of see that. That's in green, and that's going to be at this point. So it's equal to 1, 1. Just to show it a little bit different there. And then 1 minus 2x. The last part of this in black. X is equal to so it's a wild-looking function there, set up in a piecewise manner. So that is a single function. Now notice it's defined everywhere for anything greater than -1. So it's not defined at -1. It is defined at 0 because that's shaded in. It's also defined at +1, but it's not that value. It comes down to here. And then if they go from 1 to infinity, it is further defined by that function. So the domain of this function, as you can see over here, that of all elements x, that's that x is greater than -1. The range is interesting. The range is a little more complicated. We can't quite write it out. We can, but it's a lot of pieces. The range for the y values, I can go from, y is less than 1, less or equal to 1, and up to less than 2. And then over here, we can see the values over here, it is essentially less than 0. So let's write the range just so you can kind of see it. I'm not going to have you do this. It's a little more complicated. So the y values over here, so we have y is anything less than 0. I can get in. So y is less than 0, or we have 1 is less than or equal to y is less than 2. I do see or because it could be either way. Notice it's not between 0 and 1. It's excluding. I will never get, if whatever x I put in, I'm never going to get anything in that band. So that's not part of it. But it shows you, how to do this. Now you can also do this on Desmos by putting this first, and then I put full colon 2x comma, then that full colon, x squared plus 1 comma, and then x greater than 1 full colon, and then here you can add that in or you can put that in separately. So that's piecewise defined functions. Yes, Ashley, question?
Hi, Professor. Can you go over how you drew each piece? Like, for example, when I was doing it with you, I put a closed at the coordinate like -1, -2, because I thought in the beginning it said -1, the x was greater than or equal to it. So then I closed it.
No, it should.
Can you just explain all that to me?
It should be. I wasn't looking carefully. I was thinking something else. When it's equal to, you have to shade that in. Why is that? Because it's equal to right there. I was just looking at the other one. And at 0, this is shaded in. Yeah, so this is shaded in. So in that case, it would be, it doesn't matter here, but the domain would be greater than or equal to -1. That's what it would be. Now, notice the y scale is not the same as the x. This is 1, and it's about 2 to 1. So this looks like y equal to x, but it's actually y is equal to 2x. Just plug in some points. For example, plug in -1 for x, I get -2 for y. -1/2 for x, I get -1 for y. So I just plug in values for x on that interval in here to get that function. Now when x is 0, I'm switching over to this parabola. And what does a parabola look like? This is nothing more. If I looked at each of these, for example, the graph of the first one is the line y is equal to 2x. The graph of that is the parabola. I'll just put it over here so you can kind of see it. Let's say this is my x and y axis. That's the first graph. The second graph over here is a parabola that looks like this. At 1, and there's my parabola. And that's the line y equal to 1 minus 2x. So it goes over here, 1 minus 2x, so it looks kind of like this. Goes through 1, then it goes through a half over here, and that's what that line looks like. Okay, so I have these three graphs. I'm not worried about that. That's just a point value. And I'm only going to graph these three graphs over these intervals. So for the first one, I'm only concerned about -1 up to 0. So from -1 to 0. So this is, I'll put it in green, the region that is satisfied for. So for the blue, I'm only going from, say this is -1, including that, up to but not including 0. So that's why this piece is just this little piece right here. In this way, I'm going from 0 up to, including 0, up to but not including 1. So I only capture this little piece over here in the graph. That's just the point. I won't worry about that. For this other one, I'm saying I go over here at 1, so here I am at 1, and down at -1, let's put it over here, 1 comma -1, so over here I'm looking at, and that's an open, so it's open circle on that interval. So what I have here is the intervals and the graph, so I just erase everything that's not on that interval. You could superimpose them all on top of one another, meaning this is not part of the function, but I'll put it as a dashed line. This is not part of the function, but I'll put it as a dashed line, meaning I don't capture this part of the other part of the parabola. And this is not a function, but I'll put it as a dashed line, meaning the solid line is part of the function, but this is not. So the solid lines is part of the function. I'm ignoring the other ones because it's not defined by that on that part of the graph. So this is essentially what it is, and you just have to be careful. You can actually put this into, if you wanted to, Desmos and have it sketch the same thing. Okay, so this just shows you how to represent a very complicated function that's defined what we call piecewise. It's defined in pieces. You can put pieces of things together like puzzles to create a different sort of phenomena. You know, this is a linear thing, and then it goes into a quadratic. It jumps up, turns on, goes to a quadratic, shuts off, and then goes down in a linear fashion in that way. These functions like this are usually, you know, man-made phenomena. Sometimes nature, we approximate them with things. For example, like if some tectonic plates slide or something, that might be, it's a slow motion and then there's a quick motion, something we want to represent for that.